Okay, so I'm just going to give a little more in-depth review of the polar lighting that we see with shadow cam, in particular looking at the photometric angles that are observed in these type of observations. So just so that we're all clear and starting from the same foundation here, there's a few angles that I'll be talking about. One is the incidence angle, which in a normal image is when the angle between the vector pointing toward the sun and the surface normal. The emission angle, which is the angle between the observer and the surface normal, and the phase angle, which is the angle between both of those. And that's under normal conditions. So you can see we have a picture of LRO here because this is under normal lighting. When we all started looking at planetary images, one of the things that is really striking is how much the incidence and phase angle really matter to your observations and how you interpret a site. These are both the same Apollo 16 landing site, and on the left-hand side you can see the region under low incidence and phase, and on the right-hand side you can see it under high incidence and phase. And so your interpretation of the surface is going to be completely different. And so now we're going to be looking at shadow cam observations, which are under even a more bizarre type lighting condition. And so there was a good overview yesterday by Mark giving an overview of the instrument itself and some of the new images that we're collecting. And most of y'all were here a few talks ago when Prashun gave a really good overview of the dynamics and lighting inside PSRs. So this is probably like one of the better analogies for what polar lighting is. So instead of having one unique light source, you have a crater rim or a topographic high that's illuminating an area inside that doesn't receive direct sunlight. And so here's a football stadium, and you can see the lighting going around and illuminating the surface. And so you have all these different angles that you have to start accounting for. So under polar lighting, you have a really diffuse light source. So this is a 12 diameter crater. And depending on where you are in the crater, the lighting angles are going to be completely different. So usually when you take a single NAC observation of normally illuminated moon, you can compare features in the same image. And if this feature looks like this, and then you see another feature that looks similar, you can say, okay, these are the same. But that's not the case here because the angles vary so drastically. So for example, here, if we're at the floor of the crater, the phase angle is going to be about 60 degrees. So because the light is basically going downwards, and then if you have a nadir viewer, you're going to be looking in this direction. And so you have closer to a 60-degree phase angle. However, if you're observing an area completely on the opposite side of the crater, the phase angle is going to be closer to 90 degrees. And so, just in one little point on the surface, you can have a broad set. The other really important thing is that for each one of these points, there's multiple phase angles, multiple incidence angles. So you have light that's coming in directly from this side, and it might have one phase angle, but then when you're looking at the other crescent part of the illuminated moon, you're going to get a different phase angle. So what we're end up doing is calculating what we call median photometric angles. And so we're calculating median incidence and median phase. And if you think about it, the emission angle, there's only one of those. So luckily we only have to calculate one of those, just like a regular image, but we have these median incidence and phase angles. And these are weighted to take into account how much light is coming from each portion of the crater wall. And in addition to just tracking what the median value is, we also track different percentiles. So like the 5th percentile, 95th percentile, what the standard deviation is, what the range and phase angles are, and things like that. And so here on the upper right-hand side is an image of Shackleton Crater taken with shadow cam. And on the bottom, you can see the median incidence and median phase. And if you look closely, you can see that, there are going to be some drastic changes just within a few meters of what the incidence and phase angle look like. So the phase angles and everything changes as a function of time, of course. And so this is the same crater that I looked at before, but under different subsolar latitudes and subsolar longitudes. So for all these, the sun was held fixed on the horizon, 1.5 degrees above, but then the subsolar longitude is being shifted 20 degrees. And so you can see that over this little 6-day period, we collect this set of observations here at the bottom, and you can see how the phase angles progress around the crater. And so if the orbit is overlapping that crater multiple times over that course of that week, you can actually watch the phase angles change over time and get some really cool observations and try to learn more about how the surface is actually reflecting the light. You know, is it due to the incidence angle and emission angle affecting the roughness, the composition of the surface, and trying to resolve some of those features just based off the photometric angles. So why is this important? So LROC NAC has provided some good previews into understanding what shadowed areas might look like. And the way this was done was by collecting observations near beta 90. So when the incidence angle was near 90 degrees, if we image equatorial craters with long exposures, we would be able to see those areas in shadow by taking long exposure images. So at the top here, we have a region that's captured under direct lighting. So when the phase angle is about 30 degrees, so this is what you would normally see when you open up QuickMap. And then we also collected under secondary lighting. So incidence angles closer to 90 degrees in the directly illuminated areas, and then it's reflecting light into the shadowed terrain. And so for example, here we have illuminated crater wall on the outside, reflecting light inside. And one of the unique things that was noticed is that you have these bright mass wasting streaks going around the crater. And under direct illumination, they remain bright going all the way down the crater wall. However, when you switch over to the secondary illumination, secondary lighting, so looking at the reflected light into the PSR analog here, you'll notice that these bright areas are actually dark at the top of the crater and then only become bright again once you go back down to the crater floor. And so that's showing you, that there is a very strong dependence on whether you're going to be able to see reflectance boundaries based off the incidence emission and so forth. So in addition to just worrying about all the angles, you also have to worry about the lighting geometry. And this was shown in Prashun's presentation. So this is Faustini crater. And, the sunlight's coming from the right-hand part of your screen here and illuminating this wall and reflecting down into these, into the crater floor. And this is just a model of what the illumination might look like. And it also assumes a Lambertian reflectance inside the PSR. And, but what you can really see is that, the geometry of these craters and the way the shadows play a role in how the surface is illuminated. So if you're near the crater wall here, you're illuminated on 3/4 of the side, whereas once you move further from the crater wall, you're only illuminated from part of it. And so, you really have to think about all those type of angles and what's going on there. And so it's a little tricky and makes it pretty complicated. So in summary, we've developed a set of tools that allow us to inspect the distribution of light sources and all the different photometric angles. And this is really critical in order to understand what the reflectance properties of the surface are, as well as the morphology. This is a really great image that Mark presented yesterday showing two craters in the same shadowed area, but just depending on the lighting geometry, you can see that one looks like it's illuminated from the upper left, while the other one looks like it's being illuminated from the lower left. And so all these observations together are going to help us, really unravel what the reflectance properties are and help us interpret it. So interpret the surface. So for each point on the surface, we need multiple images, as many images as possible under all these different lighting angles to really build up this library to really interpret and analyze each individual feature. And the PSR analog craters that we've been collecting with ShadowCam over the last month or so are really going to help us decipher these polar images. So that, I'll stop there.
Perfect timing. Thank you.